Hey friends, so in today's lesson we're going to dive into characteristics of rational functions. Now some of you may be saying, okay, but we've already talked about rational functions, and we have, but we've talked about rational functions in a particular form. The form that we talked about was this form, y equals a over x minus h plus k. Okay, and so we looked at that and said, okay, well that is like taking our base function, which would be 1 over x, and it looks something like this, right? And then I'm adding, essentially, from a transformational standpoint, my a value, my h value, my k value. So my a value would be my vertical stretch. My h value would be my horizontal translation. And then on this picture, that would also show me where my vertical asymptote is. And then my k value would be my vertical translation. And on this picture, it would show me where my horizontal asymptote is. Okay, so that is one form that we've looked at. And then we've also looked at, if it's not quite looking like that form, how to long divide it out and make it look like that form. Okay, so that's what we've tackled so far with rational functions. Now, today though, what we're going to do is we're going to look at what I would call more a factored form of a rational function. And we're going to actually discover how each factor, in whether it's on the top of the fraction or whether it's on the bottom of the fraction or whether it's on both the top and the bottom of a fraction, actually create a different visual aspect of the graph. So I'm going to kind of walk you through a little bit of an investigation. You're going to want your graphing calculators handy so that you can do this along with me. This is a lesson where you do lots of pausing and you'll try and put the graph in your graphing calculator and get the same picture that I get. And then we'll answer the questions together, okay? So just have your calculator ready, have your hand on that pause button, maybe grab a cup of tea so that you can enjoy a cup of tea while we have this wonderful math journey, and be ready to answer some questions with me, okay? All right, so here we go. We've got, in grade 11, we spent some time working with rational functions and analyzing them for discontinuities. Now, discontinuities are any time where the graph won't continue, essentially. Now, we only have really talked about one type of discontinuity, and that was a vertical asymptote, okay? Remember, when something is discontinuous, that means I can't draw the whole thing without lifting my pencil. If a function is continuous, I can draw the whole thing and never lift my pencil. If the function is discontinuous, for whatever reason, there comes a point in the graph where I have to let go of my pencil. Now, the one reason we would have to let go of our pencil right now that you know for sure would be a vertical asymptote. And we know that a vertical asymptote occurs when it's a value for x that would cause the denominator to be 0 because a division of 0 is undefined, okay? Now, there are other continuities that we want to learn about. It's not just a vertical asymptote that causes us to have to lift our pencil. Sometimes a hole in the graph will actually have to cause us to lift our pencil, okay? And those holes in the graph are called points of discontinuity, okay? And so we'll dive into those as we go a little bit deeper here, okay? All right, so using your graphing calculator, graph y equals 3, x plus, or 3 over x plus 2, sorry. Now, again, just if you have, I know I've said this in other rational conversations, but just for clarification, if you have a newer Casio model or if you have a newer TI model, you want to open up your fraction first so that you can put 3 on top and x plus 2 on the bottom. If you're dealing with an older Casio model or an older TI model, you want to write that as 3 divided by and then put brackets in the denominator. So that'd be bracket x plus 2 bracket, okay? Also, if there was more going on in the numerator, you'd want that in a separate bracket as well. Essentially, it's bracket in the numerator, divide by bracket in the denominator, okay? Okay, so go ahead and pause me, graph that, and then we'll compare pictures. And you should get something that looks like this. Okay, now you're not going to visibly see those asymptotes. I've purposely drawn them in to give you that visual, but you can see that space there. So you can imagine that that's where the asymptotes are for sure. Okay, so now we're going to look at the domain, the range, the x-intercepts, the y-intercepts, and the discontinuities. Okay, so the domain will be x is a member of the reals, but it can't be -2. That's my non-permissible value. And it looks like that non-permissible value here created the vertical asymptote. And we should feel decently comfortable about that, even just based on what we've done in 20-1, that there should be a vertical asymptote there. That shouldn't be too much of a problem for you. Okay, the range is going to be real but can't be 0. So all the values of y such that y is a member of the reals, but y can't be 0. The x-intercept for this guy, there isn't one because there's a horizontal asymptote at y equals 0. Okay. For the y-intercept, that would be at 0, 3/2. Now, all I did there, algebraically, if I want the y-intercept, the value of x is 0. So I just plug 0 in for x, and I get out y equals 3/2. Okay. And then for discontinuities, there's only one type of discontinuity here, and it's a familiar one. I didn't want to throw too much confusing stuff at you all at once. Okay, so this one's familiar. The discontinuity is a vertical asymptote. So we say there's a vertical asymptote at x equals -2. And then there's a horizontal asymptote at y equals 0. So vertical asymptote at x equals -2, horizontal asymptote at y equals 0. Those would be your answers for discontinuities. Okay, now nothing on here tells us too much yet. With the exception of, I would want you to be comfortable to say, hey, this x plus 2 on the bottom is going to lead us to a vertical asymptote. Okay. The rest of it, we're going to kind of piece together as we go. So let's try another one. The next one I want you to try is y equals 10x over 5x plus 10. Okay, 10x over 5x plus 10. So go ahead and put that in your graphing calculator. You can pause me for a second. Okay, and then this is the picture that you should have ended up with. Now, what I want you to notice up in the top left corner of your screen there, I have written that in factored form because I want us to look at what the factors are telling us. So on the bottom, I just took out that 5 so I could see it as 5x plus 2, 5 times x plus 2, okay? So right away, I want you to say, hey, I've got another horizontal asymptote here, sorry, vertical asymptote here at x equals -2, because that's another NPV, right? Okay, so that's something I could now tell from the factored form of the equation. Okay, so let's fill in these questions together and then we'll keep looking at it. Domain, range, x-intercepts, y-intercepts, and discontinuities. Domain is going to be all the values of x except that x can't be -2. The range, well, you'd have to know where this asymptote is, and you may not, I mean, you can see it on mine, okay, because I actually drew the line in there, so you'd be pretty comfortable to say it's at 2. On your graphing calculator right now, you are just kind of guessing at 2, but it is for sure at 2. And one of the things I want to throw out at you right now as we have this conversation is, do you see a 2 anywhere in our conversation on the factored form? Now, before you all say, oh yeah, it's with the x plus 2. No, it's not. That's not the 2 I'm looking at. I'm looking at another 2. So can you see another way to get 2 there? I'm just going to let you think about that for a little bit. But for sure it is at 2. And so I want to say, let's put the domain in. All the members of the reals except x can't equal -2. And then the range is all the members of the real except y can't be +2. Now, for x-intercepts, there is one, and it's at 0, 0. Okay, so now I can find the x-intercepts just based on the equation. And now some of you are saying, of course you can, Hill, don't be an idiot. You just plug in 0 and you solve for x. And that's totally true. You can always plug in 0 and solve for x. But one of the things I want you to think about, well, actually, let's just do that for a sec. If I plugged in 0 up here, okay, let me just put some ink on here for a second. If I made that 0, okay, then I would multiply both sides by 5 times x plus 2. And 0 times anything is 0. So that actually just leaves me with 0 equals 10x. Okay, and if 0 equals 10x, what I want you to understand is this guy up here is actually telling us where that x-intercept is. Okay, so the guy on the top seems to be related to the x-intercept. And in this one, like if I kept going, 0 equals 10x, divide both sides by 10, 0 equals x. So I know I have an x-intercept at 0, 0. Okay, I also know I have a y-intercept at 0, 0. And now I want to talk about discontinuities. Okay, so I'm just going to put that into our notes. So for discontinuities, I have two of them to talk about. I've got that vertical asymptote at x equals -2, and I've got that horizontal asymptote at y equals 2. Okay, so now that I had left you alone for a couple of minutes, do you have any thought as to where that 2 for the horizontal asymptote came from? I might just throw a quick little thought at you and say, huh, isn't it interesting that 10 divided by 5 is 2? I'm just going to leave that thought with you. We'll dive into it more as we go. Okay, so exciting. Okay, let's try this guy. X squared minus 9 over x minus 3. Now, in your heart of hearts, I want you to look at that and say, hey, I can factor that. I totally want to factor that, and I totally agree with you. So we could look at that. Now, when you go to put it in your graphing calculator, because this is an investigation, go ahead and write it exactly like that. But if you're thinking about it from a factored standpoint, we're going to take that x squared minus 9. We're going to say, hey, that's a difference of squares, so that's x plus 3, x minus 3. Okay. What's interesting is when you graph this, you end up looking like a straight line, and you're like, why would I ever look like a straight line? That just makes no sense. This is the very first one that starts stressing kids out. Okay. I don't mean to stress you out. It just sometimes happens naturally. So let's go back to this factored conversation though. Think about what happens. If x squared minus 9 factors into x plus 3, x minus 3, then really what happens is, sorry, I'm just looking for ink here. My x minus 3's would divide each other out. And that leaves me with y equals x plus 3, which is just a straight line. That's the line you're looking at right now, is the line y equals x plus 3. You have a y-intercept at 3, and you're going up 1 over 1, up 1 over 1, up 1 over 1. That's exactly what that line is. Funny thing though, there's still an NPV there, right? Because I didn't divide that x minus 3 out. There is an NPV here that says x cannot be 3, because if x was 3, I would have a division of 0, and that doesn't work. But I want you to see that this is not a vertical asymptote, because if this was a vertical asymptote, you would see the graph bend towards the asymptote, just like it did here, right? The graph is always bending towards the vertical asymptotes. In this one, there is definitely no bend towards some sort of a line here. So this actually creates the other thing. It's called a point of discontinuity, and it's essentially a hole in the graph. Okay, so although you can't see it, x can't be 3. So right here, there exists this tiny hole. Now, to prove that to you, I want you to take your graphing calculator, and you all have a trace button. I want you to go trace 3, enter. And you'll notice either for the y value, it will say error, or it will just be blank to say that nothing exists there. Okay. Trace 3, enter. Try that for me so that you know I'm not just making stuff up. Okay. Okay, so what we say is we say that this simplifies to x plus 3, comma, where x can't equal 3. Now, just a little word about your communication to me. If I ask you to create equations, which I definitely will in this course, if I ask you to create a rational equation, I don't really want the simplified version here. I want this version here, because this version tells me everything I want, okay? If you choose to write the simplified equation, you can't just write y equals x plus 3. You're also going to have to add that caveat, x can't equal 3, because x still can't equal 3, right? The original equation was this guy, not the simplified version. So if you simplify it, the non-permissible value doesn't go away. That's the big thing I want you to think about there, okay? Now, with that thought, there's an additional thought. If x can't be something, if there's a hole in my graph, then there has to be a forbidden y value as well, right? Because every point has an x and a y value. So if there's a forbidden x value, there must be a forbidden y value. Well, how do I figure out what that forbidden y value is? Well, I can plug the forbidden x value into my simplified version. I can't plug the forbidden x value into my original equation, right? Because it's a non-permissible value and I'll get an error. But in the simplified version, it's not, the NPV isn't there anymore. And so I can actually plug in the forbidden x value into the simplified version. If I plug in a forbidden value, I'll get out a forbidden value. So if I plug in a forbidden input, I'm going to get out a forbidden output. Okay, so if, sorry, I need to get my mouse back working here. If x can't equal 3, then y can't equal, well, if I plug in 3, I get 3 plus 3 is 6. So that tells me there's a point of discontinuity in this graph at 3, 6. Okay, this also tells me that not every factor on the bottom of the denominator is going to create a vertical asymptote. Here, we have a factor on the bottom of the denominator, and it did not create a vertical asymptote. It created a point of discontinuity. Okay, now, this might stress you out, and this might make you say, well, how do I know whether I have a point of discontinuity or whether I have a vertical asymptote? And here's what I want you to notice. Okay, just let me get this ink off for you. The point of discontinuity happens because there's the same factor on the top and the bottom. Okay, so if a factor exists on the top and the bottom, on the numerator and the denominator of the fraction, that's what creates the point of discontinuity instead of a vertical asymptote. If the factor is on the bottom only and is not shared with the same thing on the top, if it's on the bottom by itself, that's what creates a vertical asymptote. Okay, so now from the equation, without actually seeing a picture, we understand the difference between what will create a point of discontinuity and what will create a vertical asymptote. Okay. All right, so now we're going to answer our questions, but the other thing I want you to notice is when I actually draw the graph, I need to put a hole where the point of discontinuity is. Now, obviously the hole is not that big, right? You guys are smart kids and you can think about the fact that at 3.1, my graph exists. At 3.001, for those of you approaching calculus, that would be an interesting conversation, but at 3.001, my graph exists. So that hole is actually infinitesimally small, okay? But we just draw an open circle around 3 there just to make the point, hey, there is going to be a physical hole in this graph, okay? All right, now the domain of this graph, x will be a member of the reals, except it can't equal 3. And then the range. The range is a little trickier with this guy because you have to algebraically figure out what that forbidden y value is. That forbidden y value becomes part of your range. So you got to be really, really careful when you have points of discontinuity that you account for the forbidden y value in your range, okay? Diplomas love to ask you questions where they'll ask you the range of a graph that if you just plugged it in your graphing calculator, you might say y is a member of the reals. And you might not realize that there's a point of discontinuity there. Your graphing calculator is not going to show you that point of discontinuity well, okay? It can show it to you, but it's not worth the conversation right now on how to make your graphing calculator show you the whole. You need to know that the whole exists, okay? And so the range would be all the values of y such that y is a member of the reals, except that y can't equal 6, okay? Now, for x-intercepts, we've got -3, 0. And again, remember the conversation we had in that last example? We said, hey, it's that numerator that tells us where the x-intercept is, right? Well, that numerator had, in the factored form, it had x plus 3, x minus 3, right? And the x minus 3 was shared on the bottom, and so that told us the point of discontinuity. The x plus 3 was by itself on the top. Well, if I zeroed that out, if I figured out the value for x that would zero that factor out, I get -3. That is where the x-intercept is coming from, okay? So the factor on the top by itself, like when I say by itself, I mean it's not shared on the bottom. The factor on the top by itself creates an x-intercept, okay? So already in this conversation, we've talked about the fact that the factor on the bottom by itself creates a vertical asymptote. A factor on the top by itself shows us the x-intercept, and a factor that's shared on both the top and the bottom will create a point of discontinuity, okay? The y-intercept, if I plug 0 in for x here, I am going to look at -9 over -3, which will be 3, so that's 0, 3. And then for discontinuities, we have a point of discontinuity. Do not write POD. Abbreviations are not acceptable, just like VA was not acceptable, or HA is not acceptable, POD is not acceptable. You have to write out the word point of discontinuity. Make sure you spell it right. So I have a point of discontinuity at 3, 6. Okay, point of discontinuity at 3, 6. Okay, so the next one we're going to try is y equals x squared minus 1 all over x squared plus 4x plus 3. Now, up until now, the first thing I've always been showing you is the graphing picture, right? What you should see in your graphing calculator. I want to switch this up. Now that we've had enough of this conversation, I want to switch it up to say, hey, why don't we take a look at this guy? Why don't we factor it first? And let's see if we can guess a few things based on our conversation. So when I look at y equals, oh, I'm going to just hide my big old head here for a sec because I might be in the way of you seeing that equation. So it's y equals x squared minus 1 all over x squared plus 4x plus 3. Okay, and so if I go to factor that, the top is the difference of squares. I've got x squared minus 1, so that'll be x plus 1 and x minus 1. And then I've got x squared plus 4x plus 3, so that'll be x plus 1 and x plus 3. So now I have it up in the top left corner there in factored form. Okay, so what could you tell me based on your knowledge right now? Well, I would want you to start being comfortable to say, hey, that's going to give me a point of discontinuity. Okay, I have x plus 1, that's a factor shared on the top and the bottom. So I know I have a point of discontinuity at x equals -1. Now, how would I get the y value for that? I'm just going to write this right here for a second. We're just thinking out loud right now. -1. Well, if I was to, that guy would simplify out, right? So if I was to put -1 in for x here, that would give me -1 minus 1 is -2. Over 2, right? -1 plus 3. So then -2 over 2 would be -1. So I have a point of discontinuity at -1, -1. Okay, I have a vertical asymptote. Now, don't yell at me because I wrote VA. I'm just thinking out loud right now, right? I'm not answering a question. It's okay to write abbreviations when you're just thinking out loud. I have a vertical asymptote at x equals -3, and I have an x-intercept at x equals 1. Okay. Now, you may or may not be comfortable at this stage of the game to tell me a horizontal asymptote. I'm going to tell you, do you remember the conversation a couple minutes ago where I said, hey, look, it's 10 divided by 5. Well, that ended up being leading coefficient divided by leading coefficient, right? So in this one, the leading coefficient is 1 and the leading coefficient is 1. So I'm going to wager a guess here. It's not quite a guess because hopefully you believe I know what I'm talking about. But I'm going to wager a guess right now that I have a horizontal asymptote at y equals 1. Okay. And then I need y-intercepts. I would just plug 0 in for x here, and that would give me -1/3. Okay. All right. Now, pause me and graph it. And we'll just compare the graph, okay? When you go to graph it, it's probably easier to graph in that original form. Just remember, if you have an older TI or an older Casio, you want to go bracket x squared minus 1 bracket divided by bracket x squared plus 4x plus 3 bracket, okay? Okay, this is what your graph should look like then. And in fact, everything we were just discussing does ring true, okay? I have a point of discontinuity at -1, -1. I've got that vertical asymptote at x equals -3. I've got a x-intercept at 1, 0. I've got a y-intercept at 0, -1/3. And I do have a horizontal asymptote at y equals 1. Okay, so we're going to put all that together. My domain then will be x is a member of the reals, but it can't be -1 and -3. My range, y is a member of the reals, but it can't be the two forbidden y values, right? One as your your horizontal asymptote, and one as your y value of your point of discontinuity. Don't forget that y value of the point of discontinuity. I promise that's going to come up in tests, okay? Be really, really careful of that. So my range is y is a member of the reals, except that it can't be 1 and -1. X-intercept is 1, 0. Y-intercept is 0, -1/3. And for discontinuities, there are three things I need to say. I need to say a vertical asymptote at x equals -3, a point of discontinuity at -1, -1, sorry, and a horizontal asymptote at y equals 1. Okay? So this was now, remember we started off with kind of a get your feet wet. This was a kind of dive right in and see what you can tell me, okay? This is pretty cool stuff. When you can look at a factored form and tell me all that information before you even look at a picture, that shows a lot of mathematical astuteness. So if you've been following this so far, good on you. If you've not been following this so far, it's okay. Some of this stuff takes time, okay? That's why I do videos, so that you can go back and look at it again. You can go front to back as many times as you want, okay? Until it starts sinking in and you start feeling better about it, okay? You will feel better about it as you keep practicing, I promise. Okay, so now let's take a look at x minus 2 over x squared minus 4. Okay, so you're going to look at this and say, hey, let's factor this. Well, if I factor that, that'll be x minus 2 over x plus 2, x minus 2. Okay, so let me just write that down for a sec. That'll be y equals x minus 2 over x plus 2, x minus 2. Now, you're going to say right away, hey, I've got an x minus 2 on the top and on the bottom. So that tells me I have a point of discontinuity at 2 comma something, right? 2 comma something for my point of discontinuity. Well, how do I get what it is? When I go to factor this out, or factor was a bad word there. When I go to divide that out, I'd be left with 1 over x plus 2. Okay, if I plugged in my 2 for x, I would end up with 1/4. So I know I have a point of discontinuity at 1/4. I know I have a vertical asymptote at x equals -2. Now, for those of you who have been following my conversation around horizontal asymptotes, you might be wrong here, because you might say, oh, it's 1 over 1, and so I have a horizontal asymptote at y equals 1. That's actually not true. The conversation that I've had around this leading coefficient over leading coefficient was for a specific type of equation. I didn't want to throw it all at you at once. I'm trying to be nice. Specifically, when we did the leading coefficient over leading coefficient, it was because the degree on the top matched the degree on the bottom, okay? If I took you back to, let me just clear this screen for a second for you. And I'm gonna take you back to that previous question just so that you can see. Okay, this was a degree 2 over a degree 2. Okay, in this question, this one's different because it's a degree 1 over a degree 2. They're not the same degree on the top and the bottom. Okay, in fact, the degree on the bottom is larger. When the degree on the bottom is larger, what you will find is there's always going to be a horizontal asymptote at y equals 0. Okay, y equals 0. And that actually was the 20-1 type of equation. Okay, probably your 20-1 teacher said when you dealt with rational expressions and rational functions in 20-1, maybe your 20-1 teacher said you'll always have a horizontal asymptote at y equals 0 until next year or something like that. And the reason being was because in 20-1, we always made the degree on the bottom larger than the degree on the top, okay? When the degrees are the same, that's when you start having to look at the leading coefficient over the leading coefficient, okay? So go ahead and graph this so that we can verify if everything I just said is decently true and accurate. This is the picture that you should be looking at. Okay, and we do in fact have a point of discontinuity at 2, so I'm going to throw that in. And Yeah, sorry, it's at 2 comma 1/4, and I'll that 1/4 will appear in two spots, right? It's going to appear in the range, and it's going to appear when I state the point of discontinuity. Okay, so my domain is, sorry, I'm hesitating here because I'm having mouse problems. I'm clicking and nothing's happening. Okay, so my domain is x is a member of the reals, but x can't be plus or minus 2. My range is y is a member of the reals, but it can't be 0 because of the horizontal asymptote, and it can't be 1/4 because of the point of discontinuity. For x-intercepts, there is no, listen carefully because I want to bring this back to that whole factored form. There is no factor on the top by itself. Okay, there's no factor on the top by itself. That's why there are no x-intercepts. Okay, y-intercept, I could just plug in 0 for x and I get out 1/2, so that's 0 comma 1/2. And then discontinuities, 3 statements. You have a horizontal asymptote at y equals 0, a vertical asymptote at x equals -2, and a point of discontinuity at 2 comma 1/4. Okay, you're starting to feel good? You're starting to feel awesome? Okay, determine the equation for the following. Okay, so now we're going to go reverse order, essentially. I've given you the picture. You got to come up with the equation. You want to write this in factored form, and what you want to remember is every equation that you write has an a value. So you're going to write y equals a, and then all your factors, okay? So where do I get my factors from? Well, I know I have a x-intercept at -1, and so that's going to be a factor of x plus 1 on the numerator. I know I have a vertical asymptote at x equals -4. So that's going to be a factor of x plus 4 on the denominator. I know I have a point of discontinuity at x equals 2. So that's going to be a factor of x minus 2 on both the numerator and the denominator. Okay, then I throw an a value in, and I'm going to algebraically solve for a. Now, this is important because some of you who are more astute out there are looking at this and saying immediately, well, a would have to be 2 because I have a situation here where I have the same degree over the same degree, and so my horizontal asymptote has to come from the leading coefficient divided by the leading coefficient. In order to get a horizontal asymptote of 2 then, that would have to be like 2 over 1. So a would have to be 2. That was a beautiful statement. For those of you who said all of that at me, yelling at me on the screen, great. If you are asked to determine, you have to back up your stuff. So there are 2 ways to back up your knowledge. There are 2 ways to show your work. One is writing in paragraph form everything you just heard me say. Okay, you can't just put 2 in for a unless you have something to back it up. So you would have to have a whole conversation around its leading coefficient divided by leading coefficient. And so it has to be 2 over 1. You'd have to have that conversation with me on paper. Or, which I think is the easier way, and actually I think this is the better way in one sense because I use this as a check and balance. I know it's supposed to be 2, so what I'm going to do is I'm going to write an a value, and I'm going to pick a nice friendly point for x and y, which is why that -2, -1 is there. I'm going to plug -2 in for x, I'm going to plug -1 in for y, and I'm going to algebraically solve for a. Because if I can algebraically determine that a is 2, that's going to make me feel really good that I have the right answer and everything jives. Okay, I'm going to use it more as a check and balance than anything else. Okay, so here I go doing what I just said I was going to do. So I plugged in -2 for x, and I plugged in -1 for y, and I took this out of the x minus 2 out because I don't need them, right? In solving, they're just going to divide each other out. Okay, so -2 plus 4 is 2. I'm going to multiply both sides by 2. So that gives me -2 equals -a, because -2 plus 1 was -1 times a is -a, and that means a is 2. Now, you got to be super careful at this stage. Lots of kids look at this and say, oh, yay, I'm so excited. A is 2 and I'm all done. No, you're not. The question said determine the equation. A equals 2 is not the equation, right? So just be very careful of that. Your answer, the equation, is y equals 2, x minus 2, x plus 1 over x minus 2, x plus 4. Okay, so again, it did say to write it in factored form, so we're going to leave it exactly like that. And do keep those x minus 2's there, because that tells me you know there's a point of discontinuity there. Okay, cool. All right, I like this question. The function p of x equals x squared minus kx minus 10 all over x cubed plus x squared has both a vertical asymptote and a point of discontinuity. The value of k is blank, and the equation of the vertical asymptote is blank. What are we going to do? Okay. I want to kind of think out loud with you on the board for a sec. And I want you to think about this. If we were going to write this in factored form, the very first thing I would do is I would say, hey, I could take an x squared out of the bottom, right? So I would say p of x equals something over x squared times x plus 1, right? Okay, so I know that my two important non-permissible values are x equals 0 and x equals -1. One of them is going to be a point of discontinuity, and one of them is going to be a vertical asymptote. If 0 was my point of discontinuity, I'd have to be able to factor an x out of the top, right? Because I'd have to have an x factored on both the top and the bottom in order to create a point of discontinuity. I can't factor an x out of x squared minus kx minus 10 because there's no x on the 10. So I know for sure this is not my point of discontinuity. My point of discontinuity has to come from the x equals -1. And then my vertical asymptote has to come from my x equals 0. So now I think to myself, okay, that means this guy up here has to have an x plus 1. And then it's going to have an x plus something, right? And that's going to have to end up becoming a -10 for my constant term. The only way that's going to work is that this is -10, because that would give me my -10 times 1 to get -10. Okay, which means the value of k, I would end up here as x squared plus, sorry, I didn't write that, x squared plus x minus 10x. So x minus 10x would be -9x for my middle term there, which means k has to be -9. Okay, so the value of k is -9. And the vertical asymptote will be at x equals 0. Okay. Isn't that fun? I like that one. Okay. Cool. So we'll do a quick little summary here. The graph of a rational function in factored form can be written as f of x equals the vertical stretch times the x-intercept times the point of discontinuity divided by the point of discontinuity and the vertical asymptote. All we're trying to say there is that your a value is your vertical stretch, a factor on the top by itself will always be your x-intercept, and there could be 2 x-intercepts or 3 x-intercepts, right? That's okay. A factor that's shared on both the top and the bottom will be a point of discontinuity, and a factor on the bottom by itself will be a vertical asymptote. Okay, so a vertical asymptote is a factor of only the denominator. An x-intercept is a factor of only the numerator. Okay. A point of discontinuity is a factor of both numerator and denominator. As the x value approaches a point of discontinuity, there will be a hole in the graph. Okay, that's what a point of discontinuity is. Okay, to determine the coordinates of the point of discontinuity, substitute the x value of the point into the simplified form of the rational function. Don't forget your vertical stretch. Always assume your graph has been vertically stretched. So start with that a in mind. When you're writing that factored form, stick that a there right away and then algebraically determine what a is. Okay. As the x values of the rational function approach a vertical asymptote, the y values end up going to plus or minus infinity, positive or negative. To determine which way, you can look at your table of values. In calculus, this will be a whole other conversation where we look at limits as we approach a particular number. Okay. Horizontal asymptotes depend on the degrees of the numerator and denominator. The algebraic method is to long divide like we did the other day. Okay, when I was getting you to switch from a different or an alternate rational form into that transformed form, or that transformational form, that was using long division. Okay. A shortcut to this method is when you're asked to only state the horizontal asymptotes. If you're only asked to state, and I don't need work to back you up, you can let x approach infinity. So put a really, really big number in for x and see what's happening to y. Okay, this is a shortcut if you're not asked to determine. If you're asked to determine, you would need to long divide. Okay. Another shortcut, those of you heading to calculus, you won't be able to do this in calculus, but it is acceptable in 30-1. And this is kind of what I was alluding to as we were walking through the investigation. So it's all about comparing the degree on the numerator to the degree on the denominator. If the degree on the numerator is larger than the degree on the denominator, there is no horizontal asymptote. There could be a point of discontinuity though, so there could still be a forbidden y value to think about, but there'd be no horizontal asymptote. If the degree on the top is smaller, the horizontal asymptote will always be at y equals 0. And if the degree on the top is the same as the degree on the bottom, that's where we end up going leading coefficient divided by the leading coefficient. Okay. A reminder as well, the leading coefficient would be the number in front of the term with the highest degree. So it assumes that everything, if it's in factored form, it assumes that those factors got multiplied together. Okay. All right. So I am done for now. Your homework is posted there. If you do have any questions, feel free to connect with me. And we will see you again super soon. I hope you guys are doing all okay. Connect with me if you have any questions. Okay, take care.